Okay, section 13.7, tangent planes and normal lines. Okay, so the idea is this. We have a surface, right? So suppose I have some surface out in space, so maybe it looks like this. Okay. And at any given point on this surface, we have a plane that touches it just at that single point. Now, depending on the surface, it is possible that the plane might cut through the surface somewhere else, but for the neighborhood surrounding that point is the only thing touching this tangent plane. Okay, so that's the tangent plane. And then we have a normal line, which is going to be perpendicular to that plane, right? That just shoots right through, straight down through the center, straight down through the surface at that point. So that's my normal line. And this, of course, is my tangent plane. Okay. Okay. So, one thing before we get too deep into this, or two things actually. The first thing is that we have our surfaces, we'll call them surface S. So far, up to this point, we are typically seeing them as functions of x and y. So we'll get some z value is equal to a function of x and y. So we're going to use an alternative equation for this. We actually saw this in the last section. We are going to let capital F of x, y, z be equal to, and here we're just subtracting z from both sides of this equation, be equal to f of x, y minus z, which is equal to 0. Okay, so this capital F of x, y, z equal to 0 is our alternative form of our surface S. So this is our surface S. All right, that's the first thing. Second thing, in the last section we talked about the gradient, and we discovered that the gradient is normal to the contour lines, right? Well, that's a two-dimensional image. When we have a two-dimensional gradient with contour lines in 2 dimensions, that gradient is always going to point perpendicular to those lines. Similarly, if we are working on a surface, a 3-dimensional surface, the gradient is going to be pointing perpendicular to the surface, right? So it's going to be shooting straight out through the surface. So that's kind of the cool fact. The gradient is perpendicular to the surface at any point. And in fact, it gives us the direction of the normal line. Okay, so we're going to see that here when we define our tangent plane and normal vectors. So let's do that. So definitions, let's set it up. So we're going to let capital F be a differentiable function at the point P, which is x naught, y naught, z naught, okay, on some surface S given by capital F of x, y, z equal to 0, such that the gradient is not the 0 vector at that point, such that the gradient of f at x naught, y naught, z naught is not equal to the 0 vector. Then, here we go, our definitions. The plane through P at x naught, y naught, through point P, x naught, y naught, z naught, is normal to the gradient of f at x naught, y naught, z naught. That is called the tangent plane. Tangent plane to the surface S at the point P. Okay? Now, the line through P having direction gradient of f at x naught, y naught, z naught is called the normal line. The normal line to S at P. Okay, So the equation of the tangent plane is going to be given by the following. The partial derivative of f with respect to x at x naught, y naught, z naught times x minus x naught plus the partial derivative of f with respect to y at x naught, y naught, z naught times y minus y naught plus the partial derivative of f with respect to z of x naught, y naught, z naught times z minus z naught. Oh, is equal to 0. Forgot the equal 0. Is equal to 0. Okay, so don't forget the equal 0 there on the end. I know it's off screen right now. But this whole thing, our partials times x minus x naught plus the partial times y minus y naught plus the partial times z minus z naught is equal to 0. That is going to be the equation of our tangent plane. So let's go ahead and do an example. Okay, we are going to find an equation of the tangent plane to the hyperboloid z squared minus 2x squared minus 2y squared is equal to 12 at the point 1, negative 1, 4. Okay, so we need the equation of the tangent plane. Well, first thing we need to do is figure out what is f of x, y, z. So really all we have to do is get everything on one side, leaving 0 on the other. So that's going to be z squared minus 2x squared minus 2y squared minus 12. Okay, so I'm going to need my partials, and then I'll have those partials times x minus, and I'll do that for each of these. So my partial with respect to x is equal to negative 4x. Okay, so at 1, negative 1, 4, I'm going to get that fx is equal to negative 4. The partial of f with respect to y is going to be equal to negative 4y. So then at this point, that's going to give me positive 4. And then the partial with respect to z is 2z. And at 1, negative 1, 4, that's going to give me a value of 8. Okay, so then my equation of my tangent line is going to be given by the following. Negative 4 times x minus 1 plus 4 times x minus negative x, y minus negative 1 plus 8 times z minus 4 is equal to 0. Okay, so this is the baseline here. Of course, we can simplify that. So negative 4x plus 4 plus 4y plus 4 plus 8z minus 32 is equal to 0. So we get negative 4x plus 4y plus 8z is equal to 8 from 32 would be 24. So we can have our answer in this way, or if we want our first term to be positive, we can say 4x minus 4y minus 8z is equal to negative 24. Oh, and then if we notice that we have a common factor, we can divide that out. We get x minus y minus 2z is equal to negative 6. Okay, so for me, any of these would work just fine unless I specifically told you to simplify it or not to simplify it. Any of these would work just fine. Of course, for WebAssign, it might be a little bit pickier. Okay, so now let's do an example where we're going to find the normal line to a surface. So find the symmetric equations for the normal line to the surface given by xyz is equal to 12. Okay, so then we have f of xyz is equal to xyz minus 12. Get everything on one side, leave 0 on the other. So there's our surface. I need my partials. So f sub x is equal to yz, f sub y is equal to xz, and f sub z is equal to xy. Oh, I forgot to tell you the point we're doing this at. So this is at the point 2, negative 2, negative 3. There, okay, get that in there. We need that, right? Because we need to know what are these at that point. So at this point, we have f sub x is equal to negative 2 times negative 3, which is positive 6. F sub y is 2 times negative 3, which is negative 6. F sub z is equal to negative 4. So then our gradient, oops, not little f, big F. Our gradient here then is going to be the vector 6, negative 4. Okay, and of course we could reduce that. We just need something in this direction. We could reduce that by a factor of 2 if we wanted to. That would be perfectly fine. Okay, so now we need the symmetric equations of these lines. Okay, well, we have our direction vector and we have our point. So to find the equation of a line in space, that's all we need, right? So x is going to be equal to 2 plus 6t. Y is going to be equal to negative 2 minus 6t. And z is going to be equal to negative 3 minus 4t. So we can solve each of these for t to get our symmetric equations, which are going to be x minus 2 over 6 is equal to y plus 2 over negative 6 is equal to z plus 3 over negative 4. And there we have our symmetric equations of the line normal to the surface at the point 2, negative 2, negative 3. Okay, so now let's talk about the angle of inclination of a plane. So the angle of inclination of a plane is the angle that plane forms, the acute angle. So is the acute angle the plane forms with the xy plane. Okay, and that is given by this formula. Cosine of theta is equal to the absolute value of n dotted with k divided by the magnitude of n and magnitude of k, which is equal to the magnitude of n dotted with k divided by the magnitude of n, because k is going to be a unit vector. Specifically, k is the unit vector 0, 0, 1, right? Okay, so so really what that means when we dot n with k, if we have n is equal to well, I don't want to say a1, b1, c1. Let's say that our normal vector is equal to, f sub x, f sub y, f sub z, right? And we're dotting that with k, which is 0, 0, 1. What we're going to end up with here is just our partial derivative with respect to z at that point. So that's going to be our numerator. So that's kind of interesting how that works out. But just basically just bear in mind that this is going to be, oh, and all of these are vectors. Okay, so just bear in mind that this is cosine of theta equal to the absolute value of n dotted with k divided by the magnitude of n. Put a box around that. And keep in mind that this angle is always an acute angle, so it's between 0 and pi over 2. There we go. All right, so that's going to wrap this video up. If you have any questions, as always, please let me know.